Well, thank you for the introduction and thank you for the invitation. Can you hear me at the back? The microphone is working? Yeah. Okay. So actually the reason why I took the perturbation out is because it's not in the booklet, right? So I had it in the title of a previous lecture. So yeah, this should be many-body perturbation theory and GW. So this mysterious acronym GW you've probably heard a few times now during the workshop. So now is the time to learn what's behind it. And I realized there was a talk, I think last Wednesday or Thursday, by Thomas Kurzdörfer, who actually benchmarked a lot with this method, right? So the talks in a way were in the wrong order, but I understand he's on vacation now, and they probably didn't want to bring him back from vacation to give the talk right after mine. So I guess you had to believe him at the time that this GW was something useful, and today I'll fill this with life and try and convince you that indeed it is something useful. So what I'll do in this lecture today is to sort of give you the basic principles of spectroscopy. So you've done a lot of ground state work. Now we're perturbing the ground state and we're moving to excited states. Then I'll introduce this object that is the Green's function and the closely related self-energy. And much like the electron density, these are the objects that we are then working with in that theory. And then, because we're good scientists, we will make an approximation, and that approximation will make it make the theory tractable, and that's then also what's implemented in FHI aims. And then at the end, I'll talk a little bit about why we're not actually doing this with density functional theory, right? You can do a little bit, but then there's a reason why a different theory is developed and needs to be used. So let's start with the spectroscopy. So this is mostly an experimental term, right? So you have a spectrometer, you have a method that perturbs the system, and then you record spectra. And here's a typical example of a photoemission spectrum, angle resolved photoemission, ARPES, where you have many different lines. Each one is a spectrum, and then you vary the incident angle of the light, and then you get spectra at different angles, and then you can try and extract a band structure from that. Right. But what you have to ask yourself always when you do an experiment is it actually appropriate? So was this the right experiment for the question you were asking? And is it accurate enough to determine the quantity that you want? You can see already here there's some broadening. So if I wanted to interpret this as a peak, then I need to ask myself how much does the width influence the final answer? And this is actually then where theoretical spectroscopy can help and complement, right? So this is a term that only fairly recently came about, right? So where you can try and do exactly the same as an experiment, but now in theory and in the computer, right? And again, we have to ask ourselves the same question. Is the theory, is the methodological framework that we're using actually appropriate, right? Remember the question that I posed at the beginning, why are we not doing this with DFT? And then what's our accuracy, right? Are we, again, good enough when we compare to experiment or higher level theory? Because ultimately what we want to do is not worry about these issues too much. We want to do material science, we want to do physics and chemistry, we want to do applications and calculate properties and discover new phenomena and mechanisms. So I like to go, there are many forms of spectroscopy, of course, and many related theories. Today, I like to pick the example of photoemission and briefly touch on optical absorption, and then introduce to you Green's function theory and these two approximations, GW and beta sub beta. I like to illustrate this with a few examples, and they come from the field of the nitrides. On the left here, and those are light-emitting diodes, for instance, here, that are now revolutionizing our solid-state lighting, or lasers. You can also use it for photovoltaics, of course. And then on the organic side, you have the counterpart, if you wish, in organic electronics, and you can also make light-emitting devices or light-absorbing devices like these displays here. So why are these systems still interesting? So in solid-state lighting, although we now have these LEDs, there are still fundamental mechanisms that impede the efficiency, the conversion efficiency of electricity into light, and this has all to do with brightness. And then there are a lot of issues with color variability, color stability, color mixing, for instance. And then there's still a big problem with the laser diodes. So one of the visions, as you can see, that is quite old actually, is to have a laser diode that is powerful enough to project, right? And then you can, if you have such a laser system in your cell phone, you can just use your cell phone as a projector. You wouldn't need such a chunky thing that we currently have up there, right? And this would then work with color matching or color mixing, red, green, and blue. And red and blue are available, but green is not. And this is a material science problem. So the problem that I brought along that I'll come back to is this one then, very simply. The nitrides were very good or are very good solid-state system for these applications because they're all these aluminum, gallium, indium nitride crystallize in the same crystal structure. And if you remember the talk this morning and maybe the exercise you did in the last couple of days, then we can mix these material systems and create intermediaries, right, alloys, that then have the desired properties. So the property we're after here is the band gap, and we would like it to be in this visible region for a display or an LED or laser application. And the nice thing is that the band gaps of gallium and indium nitride straddle this optical region. So if we mix appropriately, then we can go from blue to green to red. Now this is true only if the band gap of indium nitride is actually down here. Now I put a question mark there because when these materials were developed in the early 2000s, the band gap was actually believed to be much, much, much larger, right? 2 electron volts, and then this concept wouldn't have worked, or not as well. So I'll address this problem as we go along. And then we very much have the same questions for the organic electronics. So the inorganic solar cells, they're still quite expensive, so we would very much like to use organic materials, but they're very inefficient. So we're kind of trapped in this conundrum, and a lot of this has to do with level alignment and bring in charge in and out of these systems. And this is one of the questions you can address with GW, as I will show you later. Yeah, as I just said. Good, so let's come to the fundamentals of spectroscopy. So what we're talking about here is photoemission spectroscopy. The way this works is that you take your system and then you shine light on the system on your sample, right? And due to Einstein's photo effect, that hits, when this light hits on an electron, the electron takes that energy and goes into a higher quantum mechanical state. And if that state is high enough that it is in the vacuum, it can leave the sample, and then we can detect it in a detector. And if you then measure the energy of this electron, photoelectron, and you know the energy of the incident light, then you can write down a difference equation, and from that you can find out how tightly that electron was bound in the sample, and that gives you information on the occupied states of the system, right? Now, you can invert the process. You can inject electrons, right? They will trickle down to available unoccupied states, and then in the process, they emit light. This light you detect. Again, you know the energy of the incoming electrons. You measure the energy of the light that comes out, and the difference tells you the energy of the unoccupied states, or formerly unoccupied states. So this way, if you think of your band structure or your density of states as having a part that is related to occupied states and one to unoccupied states, here's a way now to probe this. This is somewhat different from optical absorption, which you may think works on the same principle as photoemission, but you're not emitting anything, right? So again, you shine in light. The electron is excited, but it does not leave the sample, right? So it stays in a previously unoccupied state. It kind of forms this electron-hole pair here. So the energy is seemingly lost to you, right? Because you've done this internal excitation, but nothing comes out. So what you then measure is basically how much does not come out, and from that you can learn something again about your system. But you can see, while this involves only really tracking one electron, here you now need to keep track of an electron in a hole. So this is a different form of spectroscopy. That's why I put a different acronym here. So I'm not actually going to talk about this part here. I just put it here to illustrate the point and to avoid confusion later in the tutorial. Claudia Draxel, who was supposed to have the talk following mine, would have talked about this. Now she will talk about it on Friday, right? So you will learn about it, but not today. Good. So let's look at this then quantum mechanically. So we can very much follow this logical process. So we start off with our system. It has n electrons, and it's in the ground state, right? So in the ground state, it will have a ground state total energy. You know how to calculate it. And it has the ground state wave function. Let's assume it's the full wave function, not the Cohen-Sham-Slater determinant. So now we bring in the light, and then we promote the electron, right? And for this, we assume it leaves the sample, so it's gone, right? So we call this here an annihilation operator. So we basically kill one electron out of that n electron ground state. So what we're then left with is a system that has one electron less, or one hole more, right? And of course, that system also has a wave function, and it also has a total energy associated with it, right? But now it has, in a sense, many wave functions and many total energies, because the system is not necessarily in its n-1 electron ground state. It can also be an excited state of that n-1 electron system. And this fact here I've denoted by S for state, right? And this will then later give us the spectrum. So then you can see here, don't know if I have it here, right? So now this difference here is very clear, right? This difference here is the energy difference that we're interested in. So that is actually the removal energy, the energy that it costs to take an electron out of the system, or as we later call it, the excitation energy. And then this matrix element that we now get is then the probability amplitude for removing this electron, and it already looks like a wave function, so later we will call it the wave function of this process. And then in inverse photoemission, we go through the same steps, only with adding an electron, so we then in the end end up with an n+1 electron system, right, where we have an n+1 to the neutral energy difference, and then a different matrix element, but it's of the same form. So far this all seems very logical. Now comes the leap of faith, right? That can be proven by many pages of algebra, which I spare you. So it turns out, and this is the power now, that these quantities that are just introduced, these wave functions and these energies, right, they're actually in an algebraic form of an object that we call the Green's function, right? I'll motivate this Green's function a bit more later. So we can write down a spectral representation of the Green's function, and that actually, if we have it, tells us what the exact excitation energies of the system are, and then what these transition amplitudes are. And then we can get back to a spectrum as we saw it on one of the first slides, by simply tracing over the Green's function and taking the imaginary part. So this way, if we can calculate the Green's function, we can straight away calculate the spectral function and compare it to experiment. So if you paid close attention, you might have seen that there is this eta going to 0 here, right? So if I plot this object here, what I'll get is actually just a delta function, right? And this makes sense because these are electron excitations, and the electron itself is an elementary particle. It cannot decay, you cannot break it, right? So its lifetime is always infinite. So this is somewhat contrary to our observation, that in this experimental spectrum, right, we have peak broadening. Right? So if we look here, for instance, then we can clearly identify this region here as a peak, right, and it has a certain width. Right? So how can we reconcile this now with the fact that I just showed you a theory that contains delta functions? And this is because we are not only exciting a single electron in this process, we are exciting many, many electrons, right? And then each one contributes a delta function, and they're very closely spaced in energy, right? So a lot of delta functions closely spaced in energy can actually give rise to a peak that has a finite width, right? And this is then the peak that we are after. So it is a peak, right? So so it looks particle-like, right? So we call it a quasi-particle, and then we can attribute these three fundamental factors to it. The peak position we call the quasi-particle energy, then the width here we call the inverse of the lifetime, and then there's the peak weight under the curve, and that is the weight of the quasi-particle peak in the excited state spectrum, right? So this may sound a bit abstract, so let me motivate this quasi-particle from a different perspective. So here we were very much in energy space, right? So it makes sense. But let's look at this in real space. So we have our sea of n electrons. We bring in the light. We kick out one electron, right? And then what stays behind is a hole, is a positive charge, right? And now we have positive charges and a whole bunch of negative charges. So what will the negative charges do? They will rush in, right, because they're attracted by the positive charge. So over time, if we let the system evolve, right, the electrons in the system will react to the introduction of this positive charge. And a sea of negative charge, a sphere of negative charge will surround the positive one. It will screen out the positive charge. And then around this cloud, other electrons are repelled. Right? So then over time, this system evolves, right? So the screening process is somewhat time dependent. It happens dynamically as you would expect. But now here we have something like an entity, right, that we can then identify as this quasi-particle, right? So it is an elementary particle, a hole in this case, could be, if we invert it, could be the electron. But this electron or this hole in an environment is not a hole like a bare hole, a hole on its own. It carries system information around it, so it is surrounded by electrons, right, that screen it out, right? And if we move the hole, these electrons will follow, right? So this combined entity will move through the system, right? So this is actually the quasi-particle that we're talking about, and this is the quasi-particle that is generated in experiment. It's an elementary particle that drags system around with it. So then if we wanted to build a theory for this, it would actually make sense, and this came up in Harald's talk before the coffee break, to build a theory on not the bare Coulomb interaction, 1 over r minus r prime, but on the screen Coulomb interaction, right? So if we know the dielectric function, we can just simply convolute it with the bare Coulomb interaction to get the screen Coulomb interaction, right? And this then describes how this quasi-particle interacts with the rest of the system, right? Namely via the screen Coulomb interaction. So now we're in a position to build a heuristic theory, right? So the Green's function, it can also be interpreted as a propagator for the quasi-particle, right? So it is a non-local quantity that depends on r and r prime. So we insert the quasi-particle at time, at position r, and then it moves to position r prime, and we can describe its motion with the Green's function. And then this motion, right, during this motion, the quasi-particle interacts with the rest of the system via this screen Coulomb interaction now, right? So we close the loop with the W here, and this then gives us a heuristic approximation for something called the self-energy. that we write as a product of G and W. Why is it called self-energy? Well, it is an energy that is only there because the particle is there, right? You didn't see this thing in DFT, right? So it's an energy contribution that is induced by the presence of the particle itself, right? And it kind of measures the drag that it feels going through the system. Now, why am I telling you all this? And do you believe me when I say this is what the self-energy should look like? Well, so that I motivated it from a sort of physical point of view, but it turns out that we were lucky because when you write down a full theory for this, this turns out to be an elementary part of it. Now, what we need for the full theory is basically an entry point, right? So we need to start from something that we know, and that's a non-interacting Green's function that comes out of DFT. And then we know that the self-energy is the object that takes us from this non-interacting to the fully interacting Green's function that is called Dyson's equation. So with this last ingredient, we can then go to the full theory that is known as Hedin's equations. I know it looks horrible, and I hate showing equations like this, right? Because there's absolutely no way you can absorb all this in the minute that I'm showing this. Now, the reason I'm showing it to you is so that you believe me that a formal framework exists. And if you go to this paper, you can look it up, and you can look up the derivation, right? I will come to the point very quickly, but let me just briefly say what this is. So here's our friend the Green's function, and we can construct with it a polarizability that gives us the screen-Coulomb interaction, that gives us the self-energy, which is the object that we wanted, right? And then unfortunately, there's this nasty object here called the vertex function that links all this together, and that also enters here. So this is all self-consistent and interdependent on each other, right? But if you were to be able to solve this, this is like solving the full Schrödinger equation. You would get the exact answer. Now, anytime you have something that is exact, it is also useless because it's often not tractable. It is always not tractable, right? But it is good, it is reassuring to know that such an exact framework exists, because then you can make confident approximations, right? Or systematically improvable approximations. So what approximation will we make here, right? So I don't know if anybody has any idea, if you can see it. If you have a suggestion, please raise your hand. There's some people in the audience that know this. Right? I give you a hint. So you make an approximation often out of desperation when you have an object that is so horrible that you don't want to touch it. Right? And this object that is so horrible that you don't want to touch it is this one down here, right? Because it contains this function. Not only is it the longest, but it also contains this functional derivative of the self-energy with respect to the Green's function. So let's try and get rid of this, right? In order not to despair, by simply crossing it out. So if you take this object out, off it goes, right? Then we're left with something that is very easy, right? And that's a bunch of delta functions.
I'm not the only one deleting parts.
Right. So delta functions we know how to handle. And in this particular case, they help us a great deal, because if you insert wherever this gamma was before these delta functions, it means that the gamma simply disappears. And now, this may still look complicated, but you can recognize here that the self-energy is actually now in leading order just G times W, right? So this is a theory, right, that is based on this GW approximation in leading order, right? But we also have a prescription, if we wish, to make it more complicated, right? By finding better approximations that include part of the term that we threw away or neglected, right? So here is actually now a paradigm change. So if you, I don't know if you had talks on quantum chemistry or if you're familiar with quantum chemistry, you try and do very much the same. You build up an exact framework where you add complexity by increasing the order of the Coulomb interaction that you include. Here we're doing the same, but we're working with a screen Coulomb interaction. This makes sense because we take in some system information already into account. Okay, so how does it then work in practice once we've made this approximation here? So I said we needed an entry point, and that is our DFT calculation, right? We get our Kohn-Sham eigenvalues and our Kohn-Sham wave functions. That is something you know all know how to calculate. And then we can go back to the definition of this Green's function, right? And then wherever we had these exact excitation energies and amplitudes, we can now plug in the Kohn-Sham equivalents, right? We just simply put in the Kohn-Sham energies here and the Kohn-Sham wave functions, and then we can calculate this object. Don't worry about how it's done in the codes. Those formulas usually look a bit horrendous, but this has been done now since the 80s, and it is proven to work. Once you have this object in a representation, then you can proceed down the line. Basically, you can construct this polarizability, which is then simply a product of these two non-interacting Green's functions, right? So we just simply multiply these two G0s together that we now have. Now we have another object in our computer. This will help us greatly to calculate the dielectric function. So now from first principles, we can calculate the screening function of the material. This we can then invert. Somebody had this funny idea that the screen-Coulomb interaction uses the inverse of the dielectric function, but that's just a matter of definition. Anyways, now we can calculate this object W, and now we have a G, we have a W, we get the self-energy, G0, W0. Again, with all the building blocks we have in place, we can calculate it, and then the final thing to do is extract the quasi-particle energies. This you can either do by solving this quasi-particle equation. It looks very much like the DFT Kohn-Sham equations, only now, after this non-interacting part, we have here the self-energy that sort of, if you wish, replaces Vxc that we had in the Kohn-Sham equations. So if you solve this equation in full, which is a bit tricky because the solution depends on the solution, so the wave function shows up both on the left and on the right, and here it's on the integral. Then you get new wave functions for your excitations, right? If you don't want to do that, you can say we just do perturbation theory. So we postulate that our quasi-particle wave function is some kind of expansion in the non-interacting wave functions. If we just take the 0th order, then that means that there's no change in the wave functions, and then this equation greatly simplifies, and we get this here. So then the quasi-particle energy is simply a correction to the Kohn-Sham energy, right? So for every Kohn-Sham state, we get one quasi-particle state. And what we need to do is take out whatever exchange and correlation we had in the state and replace it by what comes from the self-energy. Good. So if you work through the theory, then you arrive at a formal scaling of the system size to the power of 4. Right? So if you brute force implement this, then whenever you double the system size, you have a factor 16 increase of computer time. So this is not so good. So this is an expensive theory, right? But sometimes you just have to pay the price to do the right thing to get the right result, right? So I'm going to show you a few examples now where this is absolutely essential, and you have to do that. And in the tutorial, you do some more, but for smaller systems, so you don't run into the scaling wall. Okay. So, as I said, one advantage of this is that we're working with the screen-Coulomb interaction, but we also have exact exchange in the theory. Right? So the self-energy here, if we just multiply the Green's function not with W, but with the Baer-Coulomb interaction, you get exact exchange. And you've heard probably in numerous talks throughout this school that exact exchange is something very important to have in theories these days. But it is not Baer exchange because it's then complemented by the screening. Right? So W minus V is the screening due to the other electrons. So let me illustrate this point and the importance of this. So here's an example. It's silicon. Right? So on the left, you have the band structure of silicon in the local density approximation, occupied and unoccupied states. It looks okay. Right? All the bands are there, and they have the right curvature. All of this is dictated by symmetry, so not a big surprise. The biggest surprise is actually when you look at the band gap here, which is the difference between the occupied and unoccupied states. And that should be 1.17 in experiment, but it is only 0.5 in LDA. So that's the infamous DFT bandgap problem that you see in the Kohn-Sham states. Now, I've taken this formula, our prescription for how to correct the Kohn-Sham states, right? And I've split it up into these two parts, exchange and correlation. So let's only add the exchange part for now, right? So this is sort of like a Hartree-Fock calculation by the LDA wave functions. And look at the same thing. And now this looks bad, right? First of all, we've lost this band here. Well, it's still there, but it's a much lower energy. So we've overstretched the spectrum, right? And the band gap is now, I don't know, 6 or 7 electron volts. So ridiculous, right? Doesn't make any sense. And this is why nobody does Hartree-Fock calculations for solids, right? Now, if we then include this part that comes from the screening, right, and do a proper GW calculation, you see everything is fine now. Our band has come back from the basement, and we get a very good band gap now, right? So in this case, it's actually in very good agreement with experiment. So what this illustrates is that for solids or very highly polarizable materials, it is absolutely essential that we work with a theory that contains the screen-Coulomb interaction, that we work with a screen-Coulomb interaction, right, in the screen's function framework. Okay, so here's another example of work that we did a few years ago. So remember these blue lines that I showed you, these spectra. So these were ARPIS experiments for zinc oxide. And if you sort of look at the spectrum from the top and then color code the heights, basically, then you get this picture here. So high intensity is white and black, I think. No, it's white. And blue is sort of background. Then you get something that looks like a band structure, right? So in what I sort of, to aid your interpretation, I've superimposed the band structure that I've calculated with the GW method, and then you see that we get a very good match, right? So we are correct in the positions of these bands as well as the curvatures, meaning the effective masses, right? So this is good testimony for getting the right quantity out for the right reason. Now, these are only occupied states. Remember, photoemission only gives us access to the occupied states. We don't have information on the band gap. So band gap is actually something that this theory, GW theory, was known for, and that's very much its claim to fame, that it was very good at calculating band gaps. Now, you can measure band gaps differently. Most of the time, you get it from optical absorption, and you know the exciton binding energy, or when the exciton binding energy is small. So we do have good reference values for band gaps of some materials. So here are some. And what I'm showing you here are then computed band gaps versus experimental band gaps. So if you had a perfect theory, this would then fall on the diagonal. And you can see if we just take the LDA eigenvalue differences, then we're way off, actually, and the error is not even very systematic, right? And if we then switch actually to a different DFT functional, this exact exchange, we're doing a little bit better, actually quite a bit better. But then really the big improvement comes from GW. So if we put GW on top, do a proper calculation, we're actually very close to the diagonal here. So we actually have a high accuracy method for band gaps. Okay, so this brings me then back to this question mark, right? So if there was a question mark on the band gap of a material, can we then use this theory that we've just proven is very good for band gaps to help solve this problem? So let me illustrate this problem a little bit better. So here's a chart, like a collection of all the experimentally measured band gaps for this material in the year 2005. 2005 wasn't that long ago, right? So they measured anything from maybe 0.6 to, I think the highest value here is 2.2. And actually, historically, this information isn't in here. Historically, the older values were all up here, right? So they were above 2. So as I said, for the longest time, people believed the value for this band gap was around 2. And then these experiments became available, and then everybody started to question this old value and wondered what was going on. what was worse actually was when only these values were available, a lot of theoreticians that were running calculations for band gaps of this material tried to make their calculations give 2 electron volts, and they couldn't. They always got a lower value. And they were fudging all sorts of things, right? And in the end, it turned out everything they fudged was completely wrong because they should have aimed for this and not for that value, right? So always be careful when you do that. So some clue as to what's going on is given here by this x-axis. That's the carrier concentration of the material. So more about this in a minute. So many reasons were put forward for why this band gap might be different. So the high carrier concentration gives rise to the Moss-Bernstein effect, which gives you an effective gap that might look larger. Then impurities, point defects, or trapping centers could be what you're actually measuring instead of the real band gap. Non-stoichiometry could be a problem if your growth isn't perfected, then you don't actually have indium nitride, you have a very different material, although you might not know it. If you have oxygen in the chamber, you could actually form an oxynitride, which then could have very different properties. What was also speculated was that metal precipitates, and then you get some indium clusters in an indium nitride matrix, and you're picking up a signal from those, like maybe a plasmon resonance or something like that. And then every explanation had a theory that backed it up. So what we thought was, okay, we have density functional theory, so in the computer we can prepare absolutely pure indium nitride without all these defects, without the oxynitride, right? So really pure hexagonal indium nitride. And then if we pair it up with GW with a theory that gives us predictive power on the band gap, then we can maybe make an authoritative statement that if you had an absolutely pure material, that is the band gap you should get. Right? So this is then what we did, and here in red is the band structure. And you see the fundamental band gap in this GW calculation is 0.7 electron volts. So it is actually low, right? It is not 2 electron volts. So that was our statement, the band gap should be low. And then we went on to explain why such a variety of results was observed. This you can understand when you then picture what would happen if you had excess electrons. Say, in your growth, you introduce impurities and they donate electrons. Then you have an intrinsically doped sample. They knew it was n-type dope. They knew they had too many electrons. So where do they go? They go to the bottom of the conduction band. So you have a pool of electrons here in this well, in this bowl. And then here you can work out basically up to which energy this band is filled, given the curvature of the band and the electron concentration. You can see you start filling it up very quickly as a function of carrier concentration. Now the way the band gaps were measured was by optical absorption, right? So you make an excitation here at the gamma point, and that's how you would determine what the band gap is. But you cannot make this excitation if electrons are sitting there. That state is just simply not available. What you then have to do, or what the photon has to do, is have to find another electron that can make a direct transition further out. Like maybe if you're at 10 to the 18, you have to go beyond this to the left, right? So you do your transition out here, but then you need much more energy, right? Because the band curves away from you. It curves away from the valence band, and the valence band curves away, right? So you're measuring a band gap, you're measuring a value that is larger than the band gap, so you seemingly have a larger band gap, right? Because you don't know necessarily, you just can't measure down here, right? So what we can then do with these results is we can plot now the band gap as a function of carrier concentration using these results. And this is what you get in red here. This is our prediction for how the band gap should behave as a function of carrier concentration. And it falls right through these points. So now it is actually accepted that this was the problem. And if you find a growth method that reduces the carrier concentration, which they did here in these samples, and now they can go even lower, then you indeed find a fundamental intrinsic band gap that is of the order of 0.7, which proves the point. And luckily, this is what makes solid-state lighting possible and saves us a lot of energy. Okay, so let me come to the organic electronics. I'll only touch on a small part of it. There's more in the talk, but I probably won't have time for it. And this is related to interfaces, right? So they always, we call it organic electronics, but there's always an interface, right, to mostly a crystal or a metal or something like that. We need a contact to get charge in and out, right? It can be very thin, but it's always there. And now the community has realized that oftentimes it is actually this interface or the properties at that interface that really determine your device performance. It's not so much the organic itself. Sometimes it's the organic itself too, but the interface actually can play a very large role. So then naturally you want to understand what it does to then optimize it and tailor it. So let me draw your attention to one particular effect at such an interface that plays a large role. So here's a rendition of an interface as we would picture it in atomistic first principles theories. It looks very clean. So here we have a semiconductor molecule on top of it. In DFT, you would mostly be interested in the molecular geometry, the adsorption site, for instance, what's the shape of this molecule, how strongly does it bind, so on and so forth. But, and this is then also related to the electronic properties of this interface, and by that I mean what is the alignment of electronic states relative to each other. So let me show you the same interface that we see here in real space than in energy space. So if we have a semiconductor that we put electrons on, this will have a band gap and a Fermi level somewhere, and then the molecules or the organic gives us molecular states. They can broaden into molecular bands due to disorder or due to interaction, hybridization. Doesn't matter so much. What matters more is the distance of these states to the Fermi level, right? If you now think of transport across this interface, you want to get charge, say, from here to there. And then if you do this with an electron, then it sees this step here, so it sees a barrier, the electron injection barrier, that it has to overcome in order to get across. Now, if you write down a very simple expression for this current, then you see that this barrier shows up in the exponent, so therefore the current depends exponentially on this barrier height, which if you want to block transport is great. If you have a very high barrier, if you want to facilitate transport, then you want a very low barrier, right? So actually the distance here between these matters the most, and that's why it's called energy level alignment. You want to align the levels on the left and on the right such that they're optimal for your purpose, right? So before you can do that, you actually need to know what they are, right? And this is where GW comes in helpful again. So there's a tricky effect that gets in the way. So if we look at this cartoon first, so imagine the molecule is far away in the gas phase, right? So say we can calculate the molecular levels in the gas phase, then we send in light. This gives us the ionization potential. So we kick out an electron, we're left with a hole. So this is a charged particle in front of a surface, right? So say this is a metal surface. Now immediately alarm bell should be going off and you should say electrostatics 101, this is the image effect. And it is true. So what this charge in front of the surface does, it induces a polarization charge in the surface, so a negative charge response here. Electrons will rush to the surface, very much as we saw in the previous cartoon, and they will actually give rise to a potential, right? The so-called image potential. For holes, it looks like this. For electrons, it looks like that. And if we now complete our Gedanken experiment and move the molecule closer and closer to the surface, right, from right to left, then the electronic states will write this potential and they will change. So if we then brought the molecule all the way to the surface, we may have induced a little bit of hybridization. That's why I broadened this. But now the energy levels of the molecule have a different value than they have in the gas phase, so they got renormalized by this extra interaction that is there between the molecule and the surface. So if you wanted to include it, you know, for a metal surface, you can work this out electrostatically, and this potential has the shape 1/4z. Z being the distance to the surface. And if you work this out for a semiconductor or insulator, you see that you retain the basic shape, but you have to put in this dielectric prefactor here. So again, any theory that can capture this has to be a theory of the dielectric function. So now we're in a good position because we have a theory of the dielectric function. So we work with the screen-Coulomb interaction in W. So we should actually have a theory with GW that can capture this effect. So let me demonstrate to you that this is indeed the case. So the example that we picked was CO on sodium chloride. If you do a DFT calculation for CO in the gas phase, you heavily underestimate the experimental value. And if you then do a GW calculation, you fix this. So this is good. What happens when you put CO on sodium chloride and you do a DFT calculation for that is the gap actually goes up. It doesn't go down. The image effect tells you the gap should go down. So this has to do with some rearrangement of atoms here, some electrostatic interaction. Now, if you apply the GW theory, you see you get from 15.1 down to 13.1. So this is actually a reduction of 2 electron volts. It goes in the right direction, and it's a big energy shift, right? So imagine this. So sodium chloride has a very small dielectric constant. If you now have a semiconductor with, say, 12, or a metal with a very high dielectric constant, this reduction will be several electron volts larger, can be up to 6 or 8 electron volts. So this is a very large effect, right, that you're missing if you don't include this. And this is actually a problem why almost no DFT, I'll say this outright, no DFT calculation for this level alignment is correct, full stop, if you don't include this effect. Right. And there are now ways of including it because GW calculations for interfaces are still too expensive by putting these potentials in the calculation. Let me prove to you that this really was the image effect, and for that we did a calculation where we repeated this Gedanken experiment. So we put sodium chloride on germanium to create another interface. Germanium has a higher dielectric constant, gives us a stronger image effect, and then put the CO on top of that. And then in the sandwich structure, we increased the thickness of the sodium chloride layers from 2 to 3 to 4 to 6, whatever. And then what you see is the sodium chloride, the CO moves further and further away from the germanium, so it rides the image tail up, right, in energy. Right? So what you would expect now is that the CO gap in this compound system becomes dependent on the thickness of the sodium chloride layer. And this is indeed the case, right? If you look at the GW results, we have the smallest gap for the thinnest layer, so when the CO is closest to the germanium, and then as we move it further away from the germanium, the gap of CO increases until eventually we'll recover the 13.1 for just pure sodium chloride. Right? So this proves that this renormalization is there and that it really is the image effect. Again, if you had done this just in DFT, then you would have missed it completely. There's no dependence on this, or if there's a slight dependence, it goes in the wrong direction. Okay, so briefly, let me say a few words about what is wrong with DFT. So in exact DFT, at least for finite systems, we have a theorem that says that the highest occupied Kohn-Sham state is equal to the ionization potential. This you can prove by considering the asymptotic form of the potential. But this is the only thing we have. For no other state can we prove such an exact relation, right? The only thing that you can do is invoke Janak's theorem that tells you that the difference or the change in total energy is related to the eigenvalue. You can integrate this, and then you arrive at your total energy difference for the excited state that already came out of the sort of former theory. So this you can then use by setting this S here to the ground state, right? And then you can extract 3 quantities exactly if you want. So if you work with the n-1 electron state, you get the ionization potential exactly from this total energy difference. If you add an electron, you get the electron affinity exactly, or the difference of those gives you the gap of the system, right? So these are just total energy arguments. You know, DFT in principle gives you the exact total energy, so therefore this must work, right? Here's an example that there's a big difference between eigenvalues and total energies. This is all related to the self-interaction error that you've heard about last week. So here for atoms, this is illustrated if you look at the total energy difference. For ionization potential of atoms, they agree much better with reference values, this is an LDA I think, than the LDA eigenvalue, right? So in principle, this is an okay way to proceed using total energy differences. There is a problem though, because I said this is only justified for differences of ground states. So if we wanted access to any other state, we couldn't really do that, right? So then you would have to implement constraints that constrain your electron in a given state that isn't the ground state, and this constraint is not clearly defined, and it might affect your energy adversely. And then what is worse is that excited state densities are not unique. Right, this is this one here. And then it's actually also kind of tedious to do a separate calculation for every state. Imagine a band structure where you have thousands of points. That means thousands of calculations. Okay, they're cheap. Another point that is related to this delocalization error is coming back to this difference between the Kohn-Sham eigenvalue and the Kohn-Sham, the total energy difference. So here, I don't know, this is from a system that also Thomas Kurzdorfer showed, a polymer. What I'm showing you here is, again, the ionization potential calculated as a total energy difference. Now, as a function of the length of this polymer. Right? So initially, this delta SCF approach gives us very good ionization potentials, and then they decrease down, and eventually you get the same as you do from a Kohn-Sham difference. So if the electronic state becomes infinitely delocalized, then this delta SCF approach breaks down, and you get the same as from the eigenvalues. And in fact, the real answer should be up here. And this is, again, related to the delocalization or self-interaction error that you heard about last week. So the last thing I wanted to do, and then I'm done, is to briefly talk about the band gap problem. So having realized this here, that for infinite excited states, for infinitely delocalized states, as you would find in a solid, we have a problem. Then if we wanted to calculate the gap of a solid as a function, as a difference of total energies, then we would have a problem. So in principle, you could write it this way, but then it is actually hard to calculate these total energies for the solid, right? So there are problems related to the homogeneous background you have to introduce when you add an electron, and there are problems with this delocalization error. So although it looks nice on paper, it doesn't actually work. So you have to rely on the Kohn-Sham eigenvalues, and there's a problem with those also, and this is then my last slide. So in principle, what you should do is calculate, start from the Kohn-Sham eigenvalue of the neutral system, the highest one of that, and then add, again, the highest one of the n+1 electron system, right? So in principle, these are actually exact, so that should work. But that's not what you do in practice. What you do in practice is you stay with the neutral system, right? And then you take the highest eigenvalue, highest occupied eigenvalue, and then you go to the next one. So this would be the LUMO, or the bottom of the conduction band. Right, so this is what we do in practice. This is the Kohn-Sham gap. So I got to this by adding and subtracting this term in the middle. So this is what we started off with. And I added 0 to it. So actually what you realize is there is another contribution here that corresponds to Kohn-Sham eigenvalues of the same number, but for, in this case, a charged system, and in that case, a neutral system. So that same state, actually, but in a charged and a neutral system. So this is what's missing, right, if you just look at the Kohn-Sham gap. So let's analyze this term very briefly, and then I conclude. So as we add an electron to a solid, the density won't change very much, right? So we have 10 to the 23 electrons. We add one more. Not much is going to change. So that means the Hartree energy is not going to change much, and the external potential is not going to change. So the only thing that then can make a difference is the exchange correlation potential, right? And it turns out that this will change discontinuously as you add this one electron. As you add an infinitesimal amount of charge to the system, you get a jump, right? And whenever you have such discontinuities, it's very hard to include them properly in the theories. So it turns out that if you wanted to use the Kohn-Sham gaps to make a prediction for the band gap, you need to add this term. And to estimate this term, you need a self-energy again. So it's a catch-22. But this is missing from most, at least local or semi-local DFT functionals. And this then explains why we are way down here with the Kohn-Sham eigenvalues when we should actually be up here. So a large part of this difference between the blue squares and the straight line is due to this derivative discontinuity. Okay, so this brings me to the end of my lecture. So I've introduced to you the basic principles of electron spectroscopy and introduced Green's functional self-energy to you. Then I've shown you the GW approximation to the self-energy and given you a few cases where this really gives us access to the physics we're really interested in. And then I've talked a little bit, although very quickly, about the pros and cons of DFT for excitation energies. Okay, thank you for your attention.